Hello. In Lab 7, you are making dibenzalacetone, which is actually this molecule right here. And before we get started on the lab, as always, I'll give a short pre-lab lecture. But then after my pre-lab lecture, you'll be given a short quiz, maybe 8 minutes, worth 5 points out of your pre-lab notebook entry. So 5 points will come from the quiz, plus another 5 for your pre-lab entry, pre-lab notebook. This is the first time that we have a pre-lab quiz, so I do want to give you a couple of hints on what might be on it. Obviously, not all of these questions will be on it because it'll be a pretty short quiz, but you need to know how to draw the mechanism. That's pretty standard. You should know how to draw the mechanism for any reaction that you do in the lab. And the mechanism that I showed you in another video, I think I have it here, okay, is 10 steps. But I'm not going to ask you for all 10 steps. I'll pick out maybe 1 or 2 steps, and I'll draw the starting material and the final, either final product or the intermediate that I want you to go to. So for this first problem, hopefully this looks familiar. This here is your product, dibenzalacetone. But I'm not starting from the acetone and benzaldehyde that you see in your procedure. This is after the 5th step. So this molecule here is the first, aldol condensation. You know, your reaction actually does 2 aldol condensations. This is the product of the first, and then you do the aldol condensation again using now this carbon as the alpha. And as usual, this carbon you're going to attack. So this is 5 steps. If you want to go over those 5 steps in drop-in hours, we can. 5 steps. Those 5 steps are actually in the video for the mechanism. It's actually starting right here. So 1, 2, 3, 4, and 5 to get the final product. Okay. Again, I'll be as fair as possible. You know, I might start you out, let's say, here. And I'll ask you, how do you kick out this OH? Well, if I start you out here, it's 2 steps, right? And so that's also another possibility. I'll start you at some intermediate, and I'll give you some final target. Okay. Problem number 2. You know, in the previous weeks, students are not really understanding, you know, what reagents they're using, or they're very slow to kind of correlate their procedure in their notebook with what's available in lab. Like, where are those solutions? And so I want us to be a little more prepared to know, okay, if I'm going to use methanol and ethanol, how does that look labeled on a bottle or abbreviated? And here we have methanol, and you should know the formula. This is pretty fundamental. Methanol is CH3OH. Ethanol is ethyl with an OH, alcohol. And that is part of your solvent mixture that you're running the reaction in. And so you're going to have to pick up, 10 milliliters of a methanol-ethanol mixture. So, this problem really is saying that you got to know the names of the chemicals and what they look like, right? Your starting material is acetone. You should know what acetone looks like. Plus benzaldehyde. Benzaldehyde is an aldehyde with a benzene ring. You should know how that looks like. So don't be surprised if I ask you to draw the chemicals that you'll be using. The good news is that this is open notebook, so you could use your lab notebook, but you cannot print out the procedure. You cannot print out any of my handouts or screenshot any of my notes. Now, if you take notes on the videos, then yeah, you could use your notes to help you out. So hopefully this encourages you also to be very conscious of what you're taking notes on, or to be very meticulous with your pre-lab notebook entry. So it's helpful when you take this quiz. Number 3, calculating the RF value. So I put the TLC on its side to save space. I think people are getting confused, and I've tried to mark this wrong if you got it wrong on previous post labs. The RF is A over B. Okay, it's a decimal. And what is A? You find the middle of your spot, okay, and you start from the origin. That's A. And what's B? B is from the origin to the solvent front. You notice that we do not start at any point, either for A or B, we do not start at the bottom of the TLC plate. You always start from the origin, because this is a measure of how far up relative to the solvent. So is it 50% the 50% the distance, or is it 75%, or is it 20%? But it'll be given as a decimal. So if it moves if it moves about, well, let's estimate this one. So A is about what? It's about 2/3 of the way that B traveled. So this is around 0.66. 0.66, about 2/3 of the way that the solvent front traveled. It doesn't make any sense to start any measurement from the bottom, because you're looking at the like I said, the percentage of how the spot traveled relative to this distance right here. Okay, I'll ask you to use centimeters, part of the ruler. So where's that? Use the centimeter side, and probably I'll ask you to show your calculations to the 10th of a centimeter. So that's one place past the decimal point. Okay? Number 4, circle the most acidic hydrogen. If 2 are tied for the most acidic, circle both. Okay. Maybe you don't see it right away. Let me simplify this drawing. Okay? You could always do that on a scratch sheet of paper or on the quiz itself. But we have this. Okay, if I remove all the hydrogens, well, except for this one here. I usually draw that one. But what's special about the aldol reaction is that you're deprotonating the alpha carbon. You're deprotonating the alpha carbon. So these two are the most acidic. Okay, it's definitely not the aldehyde hydrogen, and it's definitely not any of the hydrogens on the ring. It's the hydrogens on the alpha carbon. And we know why, because when you deprotonate, let's say we have this deprotonation, right? Let's say we had acetone. So here's acetone, that's CH3. Let me draw this a little bit better. No need to rush. CH3. And we deprotonated with NaOH. So now we have NH2, and we have this negative. Well, that hydrogen is a little more acidic than the other hydrogens because you have resonance. Oops. Resonance. Okay, what's the resonance? Shift that down, and you shift this up. Okay? And you know me, if you saw that video on the mechanism, I prefer people draw the O-enolate. So this is the O enolate. This is the C enolate. They're both enolates. Resonance are two different ways, in this case, to represent the same molecule, the enolate. But we have two different forms, the C enolate and the O enolate. Okay, did we lose track of why I'm talking about this? We're looking for the most acidic, and again, this is the most acidic hydrogens, because when we deprotonate, the anion is resonance stabilized. Okay, and so we know this. The more acidic hydrogen gives you a stabilized conjugate base. Stabilize. The more stable your conjugate base, the more acidic the acid it came from. Okay? All right. The trick is to redraw this so you could easily interpret it. Next. Oh, I didn't draw this properly. We had a methyl group right on this carbon, but it doesn't matter. There's nothing special about the beta hydrogen or the alpha beta or the gamma hydrogen. It's the alpha hydrogen that is the acidic one. Number 5. Which molecule is the most polar and which is the least polar? We notice that all 3 of them have 1 oxygen. Okay, and we know that that oxygen has a partial negative, which renders the carbon next to it partial positive. So they all have the same type of dipole. It's just that this molecule all the way on the left has a lot of nonpolar CC bonds and CH bonds. So CC single and double, and a lot of CH bonds. Those are nonpolar. And so we grossly outnumber the dipole versus the number of nonpolar bonds we have. And if we look here in the molecule next door, we have less carbon bonds and carbon-hydrogen bonds than we have for our first molecule. And if we go even further down the line, we have even less. So it's like the ratio of oxygen to carbon is getting less and less. Well, this molecule here, all the way on the left, is the most, I don't want to say non-polar actually. I'll say it's the least polar. I don't like saying a molecule is non-polar because basically all molecules can be polar, even if it's just due to London forces. So I'm not going to use the word non-polar, except when describing the bonds. The bonds are non-polar for sure, right? You've heard of non-polar covalent bonds, but I wouldn't say a molecule is non-polar. I would just say the molecule is the least polar. And this one here is the most polar. Understood? Okay, and what am I setting you up for? By forcing you to study this a little bit before the lab, I want you to think of the different side products you might get, and how do we predict they will run on a TLC plate? Okay, the TLC plate depends on the polarity. The more polar the molecule, the less it will travel. And so if we think that we have these impurities, for instance, this is your final product, but if we have this as an impurity, well, this molecule is more polar, and it wouldn't travel as far up the plate as this molecule here. And that's why I want to test this before lab, so you have an idea what to expect on a TLC plate if you think there's any impurities. Look at this, benzaldehyde, our starting material. What if we have excess benzaldehyde that didn't react and we weren't able to purify? Then we would think that this is the one that travels the least up the TLC plate. So we'll say this is probably the lowest RF value, right? It travels the the least amount, or the least distance. The final problem example is here, number 6. Again, this is the last page on your lab procedure, page 6. This is asking which molecules cannot be converted to an enolate. And in the procedure, or in the handout, let me see if I said it. I have these pink phrases, and these pink phrases are phrases that when I was taking this class, these are phrases that I memorized so I wouldn't get them, backwards, or I wouldn't forget them, because they help save me a lot of, avoid silly errors. And so one of them is enolate. This one right here. Page 3 of your lab procedure. There has to be at least one alpha hydrogen for an aldehyde or ketone to be an enolate. And in the mechanism I mentioned, right, that this molecule benzaldehyde cannot be an enolate because you can't deprotonate the alpha carbon. There is no hydrogen here. You have to deprotonate acetone, one of these two alpha carbons, and remove one of the protons. So I call this molecule here enolizable, and this molecule not enolizable. Okay, and what's important about having the enolate? That's the attacker in your mechanism. Okay, so let's go back to that problem here. So again, I said which cannot. So we're looking for who does not have any alpha hydrogens. Okay, so here's alpha, 2 hydrogens. Here's alpha. Okay, I'll mark all the alphas actually. The one on the left, no hydrogens, but the one on the right, 3 hydrogens. Take a look at this one here. This is an alpha carbon. Oops, there it is. No hydrogens. No alpha H. So that's not enolizable. Next, we have hydrogen there and a hydrogen here. Next, these are our 2 alpha carbons, and again, no alpha H, so that one. And then the last one, let's see, that's an alpha carbon. Oh, no hydrogens there either. No alpha hydrogen. Don't get confused. That's not an alpha hydrogen because that's not an alpha carbon. The alpha hydrogen is attached to the alpha carbons. That's not an alpha carbon. Okay, let's circle the last one because that also has no alpha hydrogens. There are 3 that are not able to be converted into an enolate. These are great partners for cross-aldol because, well, the other partner can form the enolate, and this gets, the job of these 3 is to be attacked. Not to be the attacker, but to be the attackee, right? And you're attacking, I like to put the dot. That's where the enolate is going to attack. All right. Come by drop-in hours. If I think of any other potential pre-lab quiz problems, I'll let you know in drop-in. But these are the main ones that I am concerned about that we really need to make sure that you understand before you move on from this lab course. This is the minimum that we need to be able to do for this lab.